అది బుక్ లో ఉంటుంది. Hello, good evening, everyone. Able to hear me? నువ్వు హాల్లోకి వస్తావా? ఏమేమి ఉన్నాయి? రైట్. అసలు ఇంకా స్టార్టే చేయాల. కంప్లీట్ క్లాస్. Hey. రాయడం అసలు
ఆయన పేరు బిఆర్ అంబేద్కర్.
Hey, Sohan, tuition
Hello.
లేదు.
Hello, can you hear me? Hello. Hello, can you hear me?
Yeah, sir, it's audible.
Okay, I'll start then. Here I'm just waiting for the other people to join. Anyway,
Okay, okay, sir.
they're not turning up anyway. So I'll start here. See some of the basics regarding the dialectics. Okay, so let's have a look at the dialectics, and we have a scope here actually for the students to score some marks here from the dialectics, lasers, and semiconductor physics. Okay, there are some areas, for instance, specific heat. Okay, of course, it's a bit difficult though, but lasers, dielectrics, and magnetism, and some basics from the solid state physics that can be easily be can have some scoring from the long questions or maybe like short questions. Okay, anyway, that's about the scheme. Anyway, see dielectrics. First of all, dielectric substances. What are these dielectric substances? Let's have a look. Actually, the dielectric substances are the ones which do not contain free electrons. Okay, that's the one which do not have free electrons or number of such electrons are too low. Actually, they'll have the electrons present, but those electrons are very small in number, very small in number, or maybe sometimes we even say that they are not having the electrons at all. So that's how the substances have been composed of. For instance, the examples are mica, glass, plastic, etc. Okay. Once again, the dielectrics are the ones which contain few electrons or number of electrons are very low. Okay, so that's the dielectrics. Okay, the dielectrics we should have some idea that where we generally use. Okay, mica in the iron box we use. We use the iron box to separate the anodes, anode and the cathode. Okay, that's one place. Okay, we use it. And other one is in the transformers. Where the transformers are the electricity wires. Okay, going from one place to another place and tying up a dark maroon colored one. Okay, dark rather not maroon, it's a dark brown colored. That's the dielectric substance. Okay, see, because you have to know that where the practically these dielectric substances are used. So the ones which are separating one wire with the other without conducting to the pole. Okay, so the one material they are actually studies has been made to use a material so that the while using for the current transmission, electricity transmission, the electricity should not conduct through the pole. Let us say iron pole has been used, then the iron pole should not conduct the electricity, should not. uh, Hello, can you hear me, please?
Good evening, sir.
Ah, yeah, you are able to hear me, no?
Yes, sir.
Okay. Yeah, okay. See, I'm just waiting for the other students to join. Okay, anyway, I'll start here with the dielectrics. Okay, today we'll have a look at the dielectrics. Okay, see, dielectrics are the substances which do not contain free electrons or having very less electrons. Okay, once again, dielectric substances are the substances which do not have free electrons or maybe having a very few electrons. Okay, so this is the reason why the dielectric substances are generally used as insulators, very strong insulators. Then, if the insulators are there, then what is the difference between insulators and dielectric? Is the general question. Yeah, it usually comes to the mind when we are talking about the dielectric substance. There are some certain differences which we have to know. For instance, we have conductors, insulators, and semiconductors. All everyone knows. And this one dielectric substances are kind of insulating substances, but they are very strong insulating substances. Okay, that's what you have to understand first. First of all, whenever you are talking about the dielectric substances, their characteristics, properties, and various substances we are talking about, that you have to have a clear idea of what are these dielectric substances and where they are generally used in our daily life. Okay, and further we'll go into the there. First of all, the dielectric substances in our daily life, for example, we use iron box. Okay, iron box in which the mica is used. And mica is the one where we use to separate the anode and the cathode. Okay, so that's the one of the applications we generally use when we have the dielectric substances used and near the transformer. At the transformer, the transmission of lines takes place and the connecting one pole to the other pole. Okay, so when the lines are being connected from one pole to another pole, there are some dark brown colored ones. Okay, substances which usually separates the the one pole to another pole, rather they're being tied to there so that the current doesn't pass through the pole. Okay, that's how the dielectric substances have been very much useful. And though we are trying hard to send the electricity through the dielectric substances, they don't function. Okay, the more we are trying, the more the positive and negative charges will go away from it. That is the reason why the dielectric substances has got wide application. Okay, and for example, we have mica, glass, plastic, and some of the examples. Okay, and this dielectric substances, Faraday, name of the scientist who has realized the importance of dielectrics in electrical phenomena. Okay, in electrical devices or capacitors. In capacitors, we have positive charges and negative charges. If any dielectric substance has been used in between, for instance, keep it like that, and then we have positive charges and negative charges, and the dielectric substance has been put. Then, as a result, the capacitance has been increased. He has done some experiment, and he has just used some kind of a paper-like substance, which is filled with coated with the dielectric material, and that is having the capacity to separate the positive and negative charges. Then, as a result, the charging capacity has been increased. Okay, that is the reason why the dielectric substances have got wider applications. And apart from that, the capacitor with the dielectric is greater without the dielectric. That's what it's been found. And the capacitance of the capacitor has been increased by the use of dielectric substances and maintaining large distance. Okay, so here what happens is the positive charges, negative charges being separated. Okay, not much of it won't take much space, but a little space is enough to separate the positive and negative charges. Okay, then as a result, the dielectric substances will play a very important role. Okay, and the capacitor, as I said, like capacitors, the dielectric substances are very much used. How you have to understand is that the dielectric substances will have positive charges and negative charges. Okay, the positive and negative charges will be present when we are trying to send the electricity to it. Then the gap widens. Okay, the positive negative charges gap widens. Actually, we wanted the charge carriers to free up from the nucleus, but it's not. Okay, so due to that reason, due to the unavailability of charge carriers, the conductivity does not. Okay, the conductivity doesn't express and it acts like an insulin. Okay, and it's a very strong insulin. Okay, though we are trying hard, this particular substances have the capability to just separate the positive and negative charges. As we are trying hard to send the electricity, the more we are trying hard to send the electricity, the more they go away from each other. The positive and negative charges go away from each other. So we define here the positive and negative charges being separated by some distance is said to be dipole. Once again, the positive charges and negative charges being separated by distance is said to be dipole. Okay, so here there are many kinds of dipoles, many set of dipoles. Here, positive charges, negative charges being separated by some distance, like one set, two sets, three sets, four sets, like that. Several sets are okay, in this substance. Okay, so now we will slowly move on to the various definitions first. Okay. First, to begin with the definitions, and then we will understand more. We will understand more about the dielectric substances definitions. Okay. So one of them is the dielectric substances are said to be the insulating materials, as I said, and further the electrons are all being bound to the parent molecules. Okay, and there are no free charge particles. That's what I said. There are no free charged carriers. Okay, and for the conduction we require free charge carriers. Okay, free charge carriers are
Excuse me, sir.
yes.
Uh, I think we are discussing dislocation, sir, right?
No, this is not dislocation, madam. These are dielectric substances.
Okay, sir.
And these positive and negative charges are being separated by some distance, a small distance. Okay, positive charge, negative charge being separated by the small distance. And when we are trying hard to send the electricity, one dipole is formed, and another dipole will also be formed. Another dipole forms. Like that, so many number of dipoles are being formed, and due to this reason, there won't be any chance of any conduct. So that's actually being taken place inside. Okay, and the process of making more dipoles is called polarization. Okay, and polarization, the term called polarization, and there should not be any confusion. Light polarization is different from polarization in dielectrics. Once again, light polarization is different from polarization in dielectrics. Generally, I think in your BSc, light polarization has been studied. Light polarization of light, the property of attaining one-sidedness. Okay, and that is said to be the light polarization. When the light rays passes through a crystal, then the parallel components and the perpendicular components, they will get separated. Okay, only either parallel or perpendicular components will be passed through. Okay, and that is said to be the polarization concept. Please do not get confused with those concepts. And here we are studying the polarization means the property of producing more dipoles. Okay, a dipole is a positive and negative charges being separated by okay one set of dipoles, two sets, three sets, four sets, and like that. So many sets of dipoles being produced, and the process of producing this is said to be polarization. Okay, generally these questions will be asked in the exam. Like, what is polarization? Okay, generally they will ask what is polarization. What are the various types of polarization? Okay, this is what like otherwise they will be asking about the various types. Okay, we'll come back to that. Okay, very shortly we'll try to understand. But we will know first of all what is said to be here. The basic definitions we have to know, like dielectric constant. Okay, dielectric constant is said to be what ratio between the permittivity of the medium and the permittivity of principle. Suppose if I say permittivity of the medium to the permittivity of free space ratio, if I say, then immediately you don't understand what I'm permittivity of the medium. Suppose if I say, what is this permittivity of the medium? Here we talk about the permittivity in the sense how many number of dipoles has been produced, okay, and and the permittivity of free space divided by permittivity of free space. This is what we call as a dielectric constant. Okay, epsilon r. We represent this as epsilon r. Epsilon r is equals to epsilon by epsilon naught. Okay, once again, the ratio between permittivity of the medium and the permittivity of free space. Okay, so this is said to be the dielectric constant epsilon r. Okay, epsilon r is equals to epsilon by. Okay, and sometimes they will be asking 4 to 5 definitions, and they can put it in the ESRF question. Okay, that's why you have to know all this. Next one is electric polarization. What are these electric polarizations? Suppose we have here the substance. Okay, in that we have here the positive charges. Positive charges in the sense, since then I have been telling you about the positive charges. After all, what are these positive charges? They are the core, actually. The core, rather, we can say that they are, that is nucleus. Okay, this means nucleus means surrounded by the orbits, and those orbits are occupying some electrons will be occupying the orbit, and the electrons will be moving around. Okay. Then suppose, see, if that is the case, if the atoms have been placed inside the electric field, for instance, the electric field has been applied. Electric field has been applied to a substance, for instance. Then the center of the positive charges, okay, and then what will happen is they will be having a displacement. So they will have a displacement while the that will actually go in a direction opposite to the supply. Okay, and then the negative charges will go in another direction. So this direction and that direction. Okay, the positive and negative charges will get separated. Okay, and one dipole is at the top. Okay. So here, see, we have nucleus and we have some electrons. So positive, negative, positive and negative. Here one set, another set, another set. See, like that, so many number of sets from the one atom, like more dipoles and another atom mutate. And here electrons are also. Then the positive, that one is the core. Okay, that is nucleus and the electron. So here one pair is, another pair is found. Like that, so many number of pairs will be found. And here, when the substance has been used, I mean, one derivative substance has been taken and the electric field has been used, has been applied, then as a result, what happens is the dipoles are being created. Okay, the more dipoles are being created, then as a result, the polarization has taken place. That is electric, because this polarization has been done due to the application of electric field. We call it as electric polarization. Electric polarization is quite simple. When the electric field has been applied to a substance where we have here positive charges, that means the nucleus, and we have the electric charges, that is electron, and both of them will get separated from each other and thereby form the dipole, and another set of dipole is formed, and like that, so many number of set of dipoles are being formed. Okay, then further we move on to the polarizability. What are the polarized? Then actually see, as I said just now, that the more strength we are applying, okay, the more electric field or electric field strength when applied to a dielectric substance, the more it opposes. Okay, the more it opposes. That means the polarization is all depending on field. Okay, so when the strength of the electric field has been increased, okay, when it has been increased, for instance, okay, then as a result, what happens? Has been increased. Then the strength of the induced dipole also increases. The strength of the induced dipole. Induced dipole means when the applied field has been, when the applied field has been given to a dielectric substance, then the dipole has been formed. Okay, and that's what we call it as an induced dipole. And then the induced dipole movement is proportional to the intensity of the electron. So induced dipole moment is proportional to the applied field. Mu equals to alpha. Okay, that's the polarizability. We call it as a polarizability. That means, see here, a substance, we call it as a pole. Is it polarizable or not? Is it polarizable or not? Means the substance, when applied the electric field to make a conduction, and how many number of dipoles will form, and whether the substance is said to be polarized or not, means how many number of dipoles are getting formed. And that's the ability to produce polarization is said to be polarizability. Okay. And further, we'll have more definitions. Okay. Uh, for instance, we have here to start, always start with the basic definitions. Okay. For instance, we have here the dipole moment. Okay, the dipole moment is the product of charge and distance. The product of charge and the distance between two charges. The product of charge and the distance between two charges. Q times dl. Dl is the small distance we are talking about. Once again, dipole moment we call it as. Dipole I already told you. The positive charge, negative charge being separated by a small distance, we call it as a dipole. And the dipole moment is product of charge and distance. Product of charge and distance. Okay, Q times 2L. Okay, dl we call it as. Then is said to be the dipole moment. Okay, and next one, permittivity. Permittivity is, I told you, the prime permittivity is that how much the substance can make polarizable. Okay, in some textbooks, they will also define like this: how much of the ability to get polarizable. Okay, is said to be the permittivity. Okay, in otherwise, how can we say it is the quantity which represents the dielectric property of the medium, which represents the dielectric property, how much it could get dielectric. Okay, permittivity can be usually we call it as the polarizable nature. It is having how much of the polarization, how much the polarization the substance can be with the application of the electric field, how much it can get polarizable. Okay, that is the point. Units generally Faraday per meters, okay, or sometimes we even call it as a coulomb. Okay, coulomb per Newton meter are the units for the permittivity. Okay, and further, dielectric constant. Dielectric constant is the dielectric characteristics are generally they are being characterized by the dielectric characteristics have been determined by dielectric constant. The dielectric constant or relative permittivity of medium is defined as ratio between permittivity of the medium and the permittivity of the free space. That's how just now I told you. Once again, I'm telling because I have to have a more understanding about the definition. Once again, as the ratio between the permittivity of the medium to the permittivity of the free space. How we have done this? Air is also said to be dielectric. Okay, and the dielectrics are not restricted to the substances. It could be liquid, yeah, it could be air and solid substance. Okay, and epsilon r, we call it as epsilon r is equals to epsilon by epsilon. Okay, epsilon is said to be the permittivity of the medium, and epsilon naught is said to be the permittivity of free space, and C is the capacitance. See that we can write epsilon r is equals to epsilon by epsilon naught, which is equals to C by C. And C is the capacitance of the capacitor. C is the capacitance of the capacitor with that. C is the capacitance of the capacitor with direct. And C naught is the capacitance of the capacitor without direct. Okay. And capacitance. As I said, like before, the dielectric substances are very much useful to make the capacitance more effective. Okay, more effective. The dielectric substances can be used in capacitors. Okay, and how the property of the conductor or system of conductor that describes the ability to store electric charge. Okay, how much the electric charge can be stored in a particular capacitor. Okay, that's what usually call it as capacitor. Okay, the property of conductor or system of conductor that describes its ability to store electric charge. And C is equals to Q by V. C is equals to Q by V, which is equals to A epsilon by D. Okay. C is the capacitance of the capacitor, and Q is the charge on the capacitor. Okay. Right. Then polarizability. As I said, polarizability is some certain thing. I'm repeating because you have to have a clear understanding. Polarizability can be defined in various ways. When the strength of the electric field is increased, the strength of the induced dipole also. Induced dipole, as I said, mu. Okay, we call it as a mu, and that also increases. More, that's what I said in simple words. The more you try to send the electricity through a substance, to a dielectric substance, the more opposition it will get. Okay, so the more it opposes. Okay, and here, see, here more dipoles have been formed, and these dipoles forming are all depending on the more the electric field we apply. So, in other words, when the strength of the electric field is increased, the strength of the induced dipole also increases. The strength of the dipole also increases. So, thus the induced dipole moment is proportional to the intensity of the electric. Okay, it is proportional to the intensity of the electric field. In other words, we write here mu equals alpha E. Mu equals alpha E. Okay, and further electric flux then. Generally in the exams, usually they will be asking a question to describe the dielectric constant, polarizability, yeah, electric displacement. The one what I'm talking right now is electric displacement. Okay, we'll have a discussion on the electric displacement, polarization vector, what are those? 4-5 definitions they'll be generally be asked for a question, for a 10-mark question. Okay, so electric flux density will have a look at what is the electric flux density, and or sometimes in some textbooks they may even give as they mention as electric displacement. Okay, electric flux density or electric displacement is one and the same. Okay, see, just now I told you about the polarizability, and the polarization vector is the dipole moment per unit volume. The dipole moment per unit volume. How many dipoles, okay, are being formed in a particular volume we are talking about, in a substance, a small volume we are talking about. Okay, in that particular volume, how many the dipole moment is been acting. Okay, that's what we call polarization. Okay,
Sir,
we call
in this definition, we need to explain all these 5 electronic polarization and ionic polarization.
no, yeah, I'll come back to that. See, I have not started what is it to be orientation polarization, ionic polarization, electronic polarization. That is actually, it's not just definitions. We have the theory and we have a little bit of derivations also. Okay. Here, first, basically, what I'm telling is dielectric constant. So, just the basic definitions I'm telling. Okay. Afterwards, I'll be talking about the electronic, ionic, and orientation polarization. In the exam, generally they'll be asking you to write the comparison between the 3 polarizations just now I told you. Okay, so these type of 3 polarizations they'll be asking to derive. Okay, and there's one more question in the dielectric substances is Clausius-Moissac equation. Okay, there's one generally they'll be asking to understand the Clausius-Moissac relation. You have to know about the 3 types of orientation. Okay, that's one thing. And basing on the three polarizations, the Cauchy-Moussetti relation has been written. And also you have to know about the internal field strength, internal field rather, local field. Okay, what is it to be local field in dielectric substances? How do you calculate the local field? A big derivation is there. Okay, so these are the important questions from the dielectric substances. Okay. Right. So let's have a look at the dielectric uh, electric flux density or electric displacement. Electric flux density or electric flux displacement, usually represented by capital D. Okay, we call it as capital D. What is this? I'll tell you. The electric flux density is given by epsilon r times epsilon naught times E. Epsilon r epsilon naught times E. E is the electric field strength. Capital E is to be the electric field strength. Okay, epsilon r is the relative permittivity and epsilon naught is the permittivity of free space. Is the permittivity of free space. Once again, capital D is given by epsilon r, epsilon naught, capital E. Okay, I can show you by writing this. Electric displacement D is given by epsilon naught, and E. Okay, and E is the field strength. Electric field strength. Epsilon R is said to be related to permittivity, and epsilon naught is permittivity of free space. Free space. D is equals to epsilon naught E. This is what I'm talking about. Okay, and E is said to be the electric field strength. Epsilon R is the relative permittivity of the material. Epsilon naught is the permittivity of free space. Okay, and further we can write the equation as D is equals to epsilon naught E plus. Okay, and since we know that D is equals to epsilon R times E, and both equations are being. Okay, so these are the equations. D is equals to epsilon E plus P, that is defined actually, and D can also be written as epsilon naught. Okay, then what we do is we name this as first and second equation, and we just equate it. It's quite simple if you just refer. Okay, and equate it. Epsilon E plus P is given by epsilon R E. This is what we will believe. Okay, so on both sides, just equate it. Okay, on both sides. Then further, we write here P. P is taken as epsilon naught, epsilon R E minus epsilon naught E. And next step, epsilon is taken as common, then epsilon R minus 1 times E. Okay, so this what P is equals to epsilon times epsilon R minus 1 times E. Okay, so this the one we have the relation. We must remember this equation. Okay, then we have, yeah, like this. There are so many definitions. Okay, next one is electric susceptibility. Okay, electric susceptibility. We call it as high E. Okay, this is what we call it as high E. Electric susceptibility we call it as high E. Okay. What is this? I'll tell you. The polarization P here, polarization, the polarization P is proportional to the total electronic flux density, E, and in the same direction. Okay, the polarization C here, generally we call it as P, the polarization P is proportional to the total electronic flux density. Okay, is proportional to the total electronic flux density and is in the same direction of electric field. Of course, it's in the same direction of electric field. Okay, so the equation can be written as capital P is equals to epsilon naught high E. This is how it is defined. Capital P is equals to epsilon naught high E times E. Okay, P is equals to epsilon naught high E times E. Okay, P is equals to epsilon naught high E times that high
Sir,
E is
please
said to be
close, sir.
electric susceptibility. That is said to be electric susceptibility. Okay, so that's the electric susceptibility. Further, we write here high E is equals to P by epsilon naught E, and that can be written as epsilon r minus 1 times E by epsilon E, and after cancellation, we'll be getting here as epsilon r minus 1. Okay, so here chi E, okay, chi E, that is electric susceptibility, is given by P by epsilon E, P by epsilon D. From the previous equation, we have P is equals to epsilon naught chi E times E. So it's been just sent to the left hand side. Then chi E is equals to P by epsilon E. It's been written, and further is equals to epsilon times epsilon r minus 1. That is the P value multiplied by E divided by epsilon E. That is remaining same. Okay, after cancellations, you will be getting epsilon chi E is equals to epsilon r minus 1. So this is very small. See definitions and all here. I'll be sending you notes. Okay, don't worry. Then if you see notes, these things are quite simple and easy. And do not miss this kind of things. Okay, epsilon chi E is said to be epsilon r minus 1. Okay, this is the electric susceptibility. They don't mention in the exam. See here, in the exam, why I'm repeatedly telling chi is said to be the electric susceptibility. I wanted the things to be registered in the mind that whenever they called as chi, that means so we were talking about electric susceptibility. Just I have seen some question papers. What they give is usually describe. Purposely they'll give as epsilon r, comma, capital P, comma, chi e, comma, d. That's it. They'll see student will be thoroughly confused of what they are supposed to write. They don't even write the electric susceptibility. No, they'll just ask you to define chi. So that's why I'm telling you here D, capital D. They'll say, what is capital D? That's the electric displacement disconnected. That's why you have to be very careful with the definition and the notation. That's okay. So further, we move on to the dielectric strength. Dielectric strength is defined as minimum voltage. Okay. Dielectric strength we are talking about is the minimum voltage required for producing dielectric breakdown. Okay. See, I'll tell you dielectric strength. Dielectric strength is actually the minimum voltage required for producing the electric breakdown. That's how we define. That's the minimum voltage. Okay, that's the minimum voltage required for producing dielectric. That is the dielectric strength. Okay, and further, the dielectric strength, decreases with the rise in temperature, humidity. Okay, the dielectric strength decreases. Okay, it decreases with the rise in temperature. That is about the dielectric. Okay, right. So we have seen now the basic definitions till now, and we further move on to the various polarization processes. Okay, what are those? As I said, electronic polarization. Okay, we have here various types: electronic polarization, we have, then ionic polarization we have, ionic polarization, then we have orientation. There are various other also, space charge polarizations and all. Have it in syllabus. See, electronic polarization, ionic polarization, and orientation polarization. These are the different types of polarization. You must have some idea, and if you just pay some attention, then that will be easy actually. Some theory part. Okay, here. And further, if we understand the three types of polarization, then we'll go for the topic called flashes. That's actually derivation, to be honest. Not much of theory, but a little bit of derivation. Okay. So we'll understand the electronic polarization. What are these electronic polarizations? Okay. It's quite an easy concept. Okay. To understand the polarization. I wanted to show it. I'll show you a picture before I go for the derivations. See, one picture if you show, then you will understand that where the duality substitution totally used. That's the place where I'm talking about in the transformers or the poles. Okay, see that's the substance we generally use to tie the wires, aluminum wires. Okay, from one pole to another pole, transmission takes place and the pole holds tight. Okay,
Sir, is
the
this related to transformer also, sir?
yeah, at the transformer. See what happens is the power lines will be passing, and the transformer it's been connected. No, no. Wires will be connected to the transformer, isn't it? And
Okay.
they use actually this kind of substances. Okay, and the poles they use. Okay, let us say some of the poles are said to be iron poles. The iron pole should not get the electricity. It should not pass. The current should not be passing through the electric pole. And how does they separate it? Suppose by accident someone touches the electric pole, you are not going to get the shock because something it is stopping from the current. That's why I'm telling again and again that please try to understand the practical application. You don't find them in your textbook. That's what I'm telling. So what they use is a type of a substance. They tie it on top. Okay, and see I'll draw the diagram and show you. This is what the electric pole is, and we have here. See this type of this method, then you will understand. See, that's a rough diagram. See, that's how the lines passes. That's the pole, and the current wires passes, isn't it? Okay, when they are passing, they say it has to be tight. Okay, they here then they'll be tying up with a substance. That is substance I'm talking about. Okay, and that's how the
Sir,
what
sir,
happens
in
is
this neutral is connected to which one, sir?
here. See, the point is not about the neutral, but here what I'm talking about is the current when current usually passes a very high voltage. A very high voltage it is when it is passing through, and still it is avoiding any contacts from that transmission line to the pole. Okay, and it is stopped. Okay, that's what you have to understand. Okay,
Okay, sir.
for the okay, it's quite interesting electronic polarization. So first of all, we'll start about electronic polarization. The electronic polarization is something like we have here positive charges and the negative charges. Okay, first you have to understand that the positive charges and negative charges are all being placed, and the electric field has been applied. Then the positive and negative charges will get separated. Okay, they will get separated. Then the electrons usually what happens is they on applying the field, the electron cloud will be okay. We have here a positive charge. It's been separated by negative charge. Okay, we call it as like once I'll draw the diagram. And this is what I'm okay. The positive charge and there's a negative charge is being separated by small distance, and that's what we call it as a dipole. Okay, and further you have to understand that on applying the electric field here, see, we have here an atom. Okay, and the electrons are being present. Okay, let us say they're all being present. Okay, like on applying the electric field, the electron cloud around the nucleus readily shifts towards the positive end of the field. Okay, see, on applying the electric field, what happens is that the atom actually, on applying field, the electron cloud around the nucleus readily shifts towards the positive end of the field. Okay, so it will be shifting towards the positive end of the field as the nucleus and the center of the electron cloud has been said. That's how it's been, let us say, this is the nucleus, and they have been, it's been separated. Let's say that this electron goes off to a distance, further distance. Okay, and this is forming one dipole, and this is within the same. See here, I have drawn the lines, so you have to understand that for the one dipole and the dipole, so many dipoles. Okay, the positive and negative charges being separated like that. So that means here what is understood is that the electrons are all being positive charges and negative charges. Okay, and here they are moving away from each other. They are moving away from each other. So the more we are trying to get close, and the more it is going out. Okay, so here the once again the displacement of positively charged nucleus and the negatively charged electrons of an atom goes off in opposite directions on the application. The field results in electronic polarization. Once again, the positive charges and the negative charges, the application field, they goes off in different directions, and with the application of electric field, and that's what we call as electronic polarization. Okay, and then when the electric field has been applied, the electron cloud, okay, forms a cloud. Why we call it a cloud means there are more number of charges. Okay, they are all being accumulated. Let us say they are being accumulated, and I'll show you here how. See here, let us say that this is how they are being accumulated. And here, do not make a mistake in your mind. Don't think in your mind that oh, accumulation is an one electron will come close to another electron and get repelled. Why it will come as a cloud? This was the question. See, a general students will be asking, and usually it comes to your mind if I say that all positive charges. Let's say I'll draw the diagram here for you, and I'll show you. See here. Now, if I ask a question that see here what I understood, what you have understood about the positive charges and negative charges. Now, what they are? Can you tell me how it is looking for you? The positive charges and negative charges, they are being separated, right? The positive charges being separated and the negative charges being separated. Okay, how you have to understand this is I'll tell you. See, they are not overlapping each other. do not understand that they are overlapping. No, it cannot be because the substance is hard. Please try to understand. There is a small gap, okay, between the charge carriers. They would have come to a particular place, but they are not overlapping with each other. They are being separate. Okay, one electron is being separate from the other electron, though they have come to a certain place, but still their positions are not overlapping with the other. That's what you have to understand. Okay, and see
Sir,
here,
the
supposing if
is
I
the positive or sir, is the positive or negative charges are going outside of the field or inside or circling?
see what happens, how you have to understand is I'll tell you. When a substance has been taken, that is the electric substance. Okay, as a dielectric substance has been taken and apply the electric field. When you apply the electric field, the positive charges. See, inside the substance you'll have atoms, isn't it? Atoms will be present. So here, as I have shown here, one of the atoms here. See in this field. Okay, here what happens here? Positive charges, negative charges. Positive charges, negative charges. That means a nucleus, and we have electrons. Nucleus and electron. A nucleus and an electron. So it's a pair. It's one pair, two pair, three pair. Like that, what happens is are there. Okay, when you apply the electric field, the more distance it will be. Okay, so that's what we call it as a dipole. The more dipoles are being formed from one atom, and another atom will be there, and from there also the positive and negative charges will be separated within that substance only we are talking. Okay, and the other thing is just now I told you again and again I'm telling you, please don't understand that they are overlapping. No, they are not overlapping. They are coming close to each other, but still they are being stuck by the binding force. Okay, the binding forces are so strong that they cannot overlap. Okay? That's why they are not able to conduct the electricity. See, the actually for the conduction of electrons, for instance, you take the case of metal. When you consider the metal, what happens? How the conduction will take place? The electrons will get freed up. Okay, more number of electrons will get freed up, and the outermost electrons, for instance, and a little bit of energy you give, maybe in the form of just room temperature, and they'll just get freed up from the atoms, and they get released, okay, from the atoms, and they are summed up to make conduction. Okay, that's how the conductivity takes place. Okay, and unlike here what happens is here when we are giving some external energy, electric field has been applied, then the positive and negative charges they get separated. The one pair is formed, and another positive and negative separate, and another pair forms. Like that, so many number of pairs are formed. And as a result, the conductivity does what happens. The more we are trying hard, the more they get separated. That's the nature of the substance. Okay, that's why it's called dielectric substance. Okay. This substance is a bit different from the insulating substance in what we are doing. The insulating substance will have free charge carriers, a bit more than the dielectric substance, a bit more than the dielectric substance. Okay, and if we compare the dielectric insulating substance for a long time, the electric forces have been applied for let us say for a very long time. Chances are there the insulating substances may conduct. But here is not really the case. That is the difference between an insulating substance and a dielectric substance. So further what I am talking about is the electronic polarization I am talking about. Then on applying the field, as I said, the electron cloud, okay, it forms a cloud around nucleus, and that will be shifting towards the positive end of the field. Okay, and further, as the nucleus and the center of the electron cloud are separated by some distance, the dipole is has been created within each atom. That's what I'm trying to tell you since then. Within each atom, you have dipoles being formed, and this the how much see here this separation. That's what I am telling you. That how much the electric field the dipoles has to be formed. They're all depending on the electric field strength. Okay, electric field strength, and further the dipole moment is the product of charge and the shift distance. Product of charge and the shift distance. Okay, Yeah, I'll show you. Yeah. Then the induced dipole is being given by mu is equals to alpha times E. Okay. Induced. Why this is written? I'll tell you. Induced moment. Okay. That's the induced moment. Mu is equals to alpha E times capital E. Mu is induced dipole. Okay. Induced dipole moment. Why the name induced? I will tell you. Induced in the sense it is actually by force, or rather by the application of electric field. The dipoles has been formed. Because the application of the electric field has been done, the dipoles has been formed. It's called induced. That's the induced dipole moment. Induced dipole moment, and E is their field. E is their field, and alpha E is the polarized, electronic polarized. Electronic polarizability. Okay, this is what the relation. Okay, mu is equals to alpha E times capital E. Okay, mu is said to be the induced dipole moment. Okay, if you take off that alpha E, then you can say that mu is proportional to E. If you write mu is proportional to E, and next step mu is equals to alpha E times E. That alpha E is said to be the constant. What that is? Electronic polarization. Alpha E stands for electronic polarization. Okay. And now it's not the end of it though, because a little bit of derivation we have to do it here. How I'll tell you. And we have here the charge density. The charge density is given by, let us say, now let us assume. Okay, so many assumptions here as usual. We have to assume the nucleus charge. Nucleus of charge ZE. Okay, so let us say nucleus is there and it's having a charge of ZE. Okay, and it's surrounded by electron. We are talking about a nucleus and electron. We are talking about. Okay, electron of charge minus Z is distributed in a sphere of radius r. Then the charge density mu is said to be here. Charge density. Charge density. Okay, mu is said to be the charge density we are talking about. Then first one once again, nucleus of charge Z is being surrounded by an electron of cloud of charge minus Z and it's being distributed in a sphere. Okay, let us say it's having a sphere of radius r. How we have to visualize this? We have nucleus here. Okay, we have a nucleus, and the electrons are being present. Okay, like this, as I show. Okay, and then he says that the nucleus, this nucleus is having a charge of Z, and the electrons are all having a cloud of charges. They are having a cloud of charge. Okay, see here, that's what I have drawn here, the dots. Those are all the electrons, and they're all being forming some kind of a cloud. Okay, kind of a cloud, you have to assume, and they are having a charge minus a d is being distributed in a sphere. Okay, it's taking a circle or a sphere and having some radius, capital R. We are not talking about in numbers. We are just illustrating from some notation. Okay, radius we are taking as capital R. Okay, and trying to write down the relation. How I'll tell you. Mu is rho is equals to minus the d by 4 by 3 because it's taken as sphere. There are some regions here that I could explain 4 by 3 pi. Okay, or further you can write minus of 3 by 4 ZE by phi r. Okay, so that's how we write the equation number 1. Rho is equals to minus ZE by 4 by 3 pi r cube, which is equals to, you can just shuffle it to write down like that, minus 3 by 4, okay, multiplied by ZE by pi r cube, ZE by pi r cube. Okay, so once again, rho is equals to minus ZE, that is the, actually I told you the charge, okay, and ZE, charge, because of the electron cloud, okay, minus ZE by 4 by 3 pi r cube, because it's been surrounded by a sphere, 4 by 3 pi r cube, okay, has been taken, and which is given by minus 3 by 4 ZE by pi r cube, okay, ZE by pi r cube has been written. Name it as equation 1 and just move on to 1. Then the external field of the intensity, let us say E, capital E, has been applied. For instance, this is the case, and the electric field has been applied. Okay. Then, as a result, then the nucleus and the electron experiences the two kinds of forces. Okay, so you have to understand that there are two kinds of forces being active. What kind of forces? One is Lorentz force. Okay, and the other one is the Lorentz is a Lorentz force. Okay, Lorentz force, and it's a Coulomb force. Actually, there are two types of forces: Lorentz force of vehicle. Then I'll show you. When the external field has been applied, the nucleus and the electron experiences Lorentz force, which is ZE times E. Okay, that is what. Okay, the Lorentz force, which is ZE times E, which is been acting in opposite direction. Okay. The electron experiences, here see a substance has been taken, because we try to understand where from where we are going. Initially, I said that we have a dielectric substance, and that dielectric substance is said to be dielectric because the charge carriers are not there, or very less in number, I said, and the positive charges and negative charges are being separated by some distance. That's what we call it as dipole. Further, more number of dipoles are being produced. That's what we call it as polarization. Fine. And coming to the electronic polarization, I'm trying to tell you here that that is the substance. Okay, we are going into the details now. Then what happens if the electric field has been applied? If more electric field has been applied, then here the two types of forces will be active. Two types of forces. One is Lorentz force, the other one is Coulomb force. Lorentz force is the one which is actually pushing the electrons out. Okay. You have to understand that Lorentz force is the one which pushes the electrons out. And whereas the Coulombian force is actually just bringing the forces, uh, e- bringing the electrons together, okay, towards the nucleus. Okay. There are, one is acting towards the direction, other one is towards away from the direction. So these are the two types of forces that are acting. Okay, Lorentz force and the Coulombian force. Coulombic force are always trying to merge two types of forces, whereas the Lorentz force always pushes things out. Okay. So that's how the two types of forces are being acting here. And
Sir,
then,
these sir, these two
yeah, yeah.
forces are these two Lorentz and Coulomb's forces are spending the same energy, or is there any?
They are equal. Very good question you asked. Okay, they are actually equal and opposite. Okay, the Lorentz force and the Coulomb force are equal and opposite. And further, we derive here, see how we write the Lorentz forces. That's what now, see, that's why I'm telling everyone here that, see, I try hard to make you to understand the theory first, understand the concept. Same thing, step by step, we are writing in the mathematical form. Most of the students doesn't pay much of attention to the theory, and straight away they go to the derivations and they'll get stuck up there. So that's what I'm telling. Very carefully listen to what I am talking about is different forces here. Coulombic force and Lorentz force. Coulombic force, we are writing the sum set of equations, and Lorentz force, we are writing the equation, and we just equate it. Okay, how we are doing. So we are writing the Lorentz force, and the Lorentz force which is acting. That's why we take it as minus. Okay, Lorentz force is taken as minus ZE times E. Okay, and the Coulombic force, which is given by ZE times E. How we have to write ZE? I'll tell you. We have here the charge enclosed. How much of the charge has been enclosed in the sphere? So you have to imagine that, oh, there is a kind of a sphere of radius that much of the sphere it is taking up. Okay, divided by 4 pi epsilon x square. Yeah. Okay, so this is the one, see, Coulomb force, how we have to define it. So we have seen the definition we have seen. I told you, what did I say about the Coulomb force? I said that some force will be acting in a particular direction, that the positive charges and negative charges. Positive and negative, what are those? The electrons and the nucleus, they try to come together by some kind of force. It's called Coulomb forces. Okay, that's what I told you. Same thing now we are putting it on paper. When and that too in derivation, mathematical form. How? I'll show you. See, this is okay. Z of E is given by Z of E. Lorentz force is given by minus ZE times E, minus ZE times E. And further, the Coulomb force is given by ZE multiplied by charge enclosed. How much of the charge has been enclosed in a sphere of radius x? We name it as small area. Okay, and that is said to be here sphere of radius. Sphere of radius, small x we are talking about, divided by 4 pi epsilon x square. Okay. And further, the charge enclosed, how much of the charge has been enclosed, which is given by charge enclosed. Charge enclosed is given by 4 by 3 pi x cube times u. That's how the charge has been enclosed over there. 4 by 3 pi x cube times rho. And all you have to do is to substitute the value. That's it, 4 by 3 and then pi x cube times minus of 3 by 4. In the previous equation, we have got the from the equation 1. Just you have to substitute there. Okay. I'll show you. This is taken from equation number 1. Okay. The rho value already we have got it. And that value you are substituting it here. Then all you have to do is to simplify it. Then you'll be getting here as minus z e x cube by r cube you will be getting. Okay. That's how we, after simplifying, cancelling in, that's what we will be getting there. And the Coulomb force has been given as ZE times 4 pi epsilon x square. Okay. And minus ZE cube by r cube, we write. Then you will be getting minus of z square e square x times by 4 pi epsilon times. Okay. So this is what we will be getting as we are just for substituting the values from the previous equation. And this is what we are going to get. And therefore, we if they are in equilibrium position, see, as you have asked that how much of force which is acting, they are equal. Okay, so in equilibrium position, the how much of force which is acting to push it out, how much of force which is acting to bring it down, bring it down, is same. Okay, and that's why we get it. That's what I'm telling you. Every step we write here is all basing on the theory. It's all linked up to the theory. So that's why I just equate it. There's an every reason. If you just see as an equation, you will never understand. Okay, that's why I'm telling you. This is one step to the theory derivation. Okay, that's how you understand and get the extra and easy to remember also. See, if you understand the theory and handling its derivations are quite easier. Okay? And E is given by here Z. After simplification, take off minus, take off Z, E and all cancellations, and which leads to Z E x by 4 pi epsilon naught. And further we extract x from it, then we will be getting 4 pi epsilon r cube E by Z E. Okay, and that's what we name it as equation 2. This is okay. See, what I have done is I have just equated, okay, in the equilibrium position, minus d times
Sir,
E.
can't able to see clearly, sir. थोड़ा ऊपर. Yes, sir.
Minus Z E times E is equals to minus Z square E square x by 4 pi epsilon naught cube. And further, capital E has been taken. See, that's what I told you. Minus minus has been cancelled, E has been cancelled, Z has been cancelled, reduced to Z E x by 4 pi epsilon r cube. Okay, from there extract x. X is equals to 4 pi epsilon r cube E by Z E. Okay, so this is the equation you will be getting. Okay, anyway, I'll give you the notes. Okay, don't worry. If I'm not busy, I'll be busy. Okay, please send me a message. Okay, I'll be sending you the text. I mean the notes I'll be sending. Okay, does the displacement of the electron cloud is proportional? See how much of the electron here. See, understand that the electrons are all making a cloud. It's been shifted. That means that shift is proportional to the electric field. Okay, so does the two electric charges plus Z and minus Z, they have been separated by distance. They have been separated by x, and the reaction of the applied field. Then a little bit of information. Further, I'll complete. Okay, so mu e further you can write as Z times x. So see, that's the dipole moment. Okay, formula we are writing. Mu e is equals to Z e times x. So already we have got x there from the equation number 2, and that we have to put it here. Okay, substitute here. So further I'll substitute it. Then Z e times 4 pi epsilon r cube E by ZE has been written, cancellations, all goes off. Then you'll be getting here epsilon or cube E, which is equals to mu E. So here see, if you take mu E is equals to 4 pi epsilon or cube is what I'll put it in a circle. See how I've circled it. Okay, and all that part is a constant. Okay, all that part is a constant, and that we name it as alpha. Okay, that we name it as alpha E times. Okay, that is electronic polarity. Okay, alpha times. Okay, the same part is said to be alpha E. Okay, and that is electronic polarity. Such an easy, isn't it? So just couple of times, if you just practice, you will become master. Okay, electronic polarizability. Polarizability. Okay. Okay, and further you can write the dipole moment. Okay, you can write dipole moment for unit volume is said to be electronic polarization. Then P is equals to N times mu e. So you have got here mu e. Mu e is linked up with electron polation, dipole moment. Okay, the dipole moment Pe is equals to n times mu. See, usually here what we do, not here, everywhere, one relation will be written, and that output will be taken and put it in next step, and that output will be taken in next. Further, same is the case here. Okay, Pe is given by n alpha e, and further n alpha e times e has been written. And we can write, finally I'll write alpha e is given by epsilon. After substitution, you'll be getting here epsilon or minus 1 by n. Okay, so finally you'll be getting here after the substitutions equating, finally you'll be getting this epsilon e, alpha e is given by epsilon times epsilon naught minus 1 by n. This is what is said to be the electronic polarization, complete derivation. So see here, looks like long, but still I tell you that we have here, just you all you have to remember is just 5 or maybe 4 or 5 steps. Why I'll tell you. See, first step, what you have to remember, there is a system, that's what I'm saying. There is a system in doing the derivations, handling derivations. First step you must remember, rho is equals to Ze by 4 pi r. Further, what we have written, Lorentz force is given by minus Ze times capital E. So, further what is written, next step is charge enclosed in the sphere of radius x by 4 pi epsilon x. And charge enclosed is 4 by 3 pi x cube. And then see, those values, 2-3 steps you must remember. And then 4 by 3 pi x cube times rho. Rho value has been taken and simplified. And further minus of Z x cube by r cube has been written. And the Coulomb force. And further you don't have to remember. Just equate it. Okay? Equate it, simplify, and the x you will be getting. And next step you have to remember. What is that? Mu is given by Z times x. That you have to remember. Substitute. Okay, simplify. And alpha e is equals to epsilon times P, you have to remember, epsilon E times epsilon minus 1. Okay, and further you'll be writing alpha E is equals to epsilon times epsilon R minus 1 by E. Okay, so this is what is said to be the electronic polarity. Okay, further in the next class, we'll have about the understanding about the anipolation. Okay. Yeah, maybe tomorrow. Tomorrow we have class at 6 o'clock. I'll take 6 p.m. 6 to 7:30. I'll take. Okay. Then we'll have ion polarization as well as the orientational polarization. If time permits, then we'll go for the flash system of the relation. Okay. That's that.
Thank you, sir.
Thank you, sir.